Bismillahirrahmanirrahim. Inshallah, we shall review here today the first part of Chapter 4. This is what we talked about last time in class. Chapter 4 is divided into two broad subjects that it covers. The first is about exponential functions. The second part of the chapter is divided into logarithmic functions. Logarithmic functions and equations. So today I'm going to review exponential functions. If you recall, exponential functions we have previously summarized as this. And exponential functions are those that have the variable, the independent variable, or the variable or the x value as an exponent. Independent variable is the exponent, because that's how the exponential function is defined. For example, y equals x squared. Well, this has an exponent too, but that's not what we're talking about. We're talking about the independent variable, x being the exponent. This is the y-intercept, like before in the linear functions, and this we've called the multiplier, or sometimes you can call it also the growth factor. I am used to calling this the multiplier. So this is the general equation of a exponential function. And we're going to review this. Y equals 2 to the x is the parent function of exponential functions. And the basic graph of here, parent function, looks like this. Okay. This is y equals 2 to the x. And the y-intercept here is 0, 1. And this we have called the vertex, or the pseudo-vertex. Because if you keep terminology kind of similar, it helps to understand this equation, similar to quadratic functions. So this is the pseudo-vertex, so to speak. It's not called the vertex, it's just the y-intercept, and that's vx and vy, so to speak. Okay, that's just for our understanding purposes. So this is the parent function, y equals 2 to the x. One important aspect of this is you have to appreciate is that this function does not cross the x-axis over here. The x-axis is an asymptote like that, so it will not cross the function will closer and closer to the x-axis, but it will actually never cross, because there's no number that you can put over here that'll make this negative. So if you put a 2 to the positive number, it'll be a positive number. If you put a 2 to the negative number, like 2 to the negative 10, it will just be 1 over 2 to the 10. It's still a positive number. So this function will never cross the x-axis, and the x-axis, in fact, is the asymptote of this function. Okay. So, and then also from this we have extrapolated our knowledge, and we said, okay, what does this look like? Y equals negative 2 to the x, and I'm pretty sure, inshallah, that you appreciate that to be the mirror image of this graph, kind of like this, artistically represented like that. Negative 1 times 2 to the x. Notice this is negative 1 times 2 to the x. It's not negative 2 to the x. That's a different story. So this is a mirror image of this graph. Also, if this is the parent function right here, we have previously also explored something like this. Y equals 5 to the x. What happens if you change the multiplier to 5? Well, the y-intercept will still be the same, but this will grow faster. It'll be like this. It will grow faster and also decrease faster. We'll go here because 5 to the negative 1 is 1 over 5. 2 to the negative 1 is 1 over 2. So this will grow faster, but also decrease faster. So for example, y equals 2 to the exponent x. That's our parent function here. Let me magnify it just a little bit. So that's our parent function with the y-intercept like this. If I zoom out, that's how it looks. Zoom in, that's how it will be. Now if I draw the other function that I just wrote down, okay, to the x like this, and this blue function is y equals 2 to the exponent x. The y-intercept is still the same. It goes up faster, and it also goes down faster like this, right? So just think about it. Would you rather be paid 2 to the x or 5 to the x or 5 to the x, because you get paid more for any given amount of time that you spend. So that's another thing that we explored. We also did something like this. Y equals 2 to the x plus 3. Okay, so this would be a vertical shift of the original parent function. So it'd be like this would be this function moved up 3. Okay, 1, 2, it'd be like this. Okay. Now it'll be like that. Notice the whole graph is moved up. Let me draw that one for you. So y equals 2 to the exponent of x plus 3. See? This whole graph, now this blue graph and the red graph, they are the same. In other words, if I drag the blue graph down, it will fit perfectly on the red graph over here. Okay. Now the key thing also understand, see, this graph has an asymptote, so does the blue graph, because the blue graph is just simply the red graph moved up. It's the vertical shift, right? So if I draw, what's the asymptote for the blue graph? The horizontal line, that, y equals 3, see? So it has an asymptote as well. So this graph is, this graph moved up 1, and therefore its asymptote will also move up by 3. The asymptote for the original graph, it's not accurate, of course, like, it's be 3 here, was the x-axis. It will be moved up by 3. Okay, so as a summary, we have explored this graph. This is the parent graph, and we have explored this graph, and then we have explored something like this, and we have explored 2 to the x plus 3. And then, as a summary, we've stated previously that you can write the general equation of exponential functions like this, okay? B times a to the quantity x minus vx, okay, plus vy. Okay, let me just put this in parentheses. So this is again the initial b, the y-intercept, and vx and vy will be the pseudo vertices, okay, of the function. So if this is the general form of an exponential function, okay, so if I give you something like this, f of x equals 2, let me make this simple first, 1 times 2 to the x minus 3 plus 4. Now this graph will have both shifts left and right. So let's try to graph this one. I'm going to keep the parent function. So y equals 2 to the quantity x minus 2 plus 3. Okay, so here's the original pseudo-vertex here. Okay, now the pseudo-vertex, okay, will be moved 2 to the right, up 3. Okay, so this is 1, 2 to the right. Okay, 1, 2, 3. Okay, so look at this. So the pseudo vertex is what's being moved here. So Vx and Vy. So move 2 to the right and up 3 will give you the new vertex. Okay, so actually, this is not the exact one I gave you, so but let's rewrite this. So f of x equals 2 to the x minus 2 plus 3 is what I graphed here, I think. So to graph this, then this is the parent equation like this, right? So in this case, the pseudo vertex is going to be moved 2 and 3 from here. So 1, 2, 1, 2, 3, because the vertex is here. Okay, so the new vertex would be 2 and 4. Okay, so this is the original vertex. So this is a horizontal shift and vertical shift. So go 2 this way and up 3 from the original vertex. Okay, and so that's the vertex. Now, this graph will also have a horizontal asymptote just like the original one. Okay, and it will be one below this because that's the way it was over here. Okay, so y equals 3 would be the horizontal asymptote because the asymptote also was moved up by 3. Very important to understand. So let me just draw the asymptote over here. So the first thing I probably should do when I do this is draw the new x-axis. Okay. So it'll be like this, see? Alright, so this would be the graph of y, or f of x, equals 2 to the x minus 2 plus 3. It's the original graph shifted 2 to the right and up 3. Okay, so this y equals b times a to the x minus vx plus vy is the general equation for exponential functions. Now we said there are two parent equations for exponential functions. The first one being y equals 2 to the x. Okay, that function, as we have already described, looks like this. And then the other parent function is y equals 1/2 to the x. See, this function models exponential growth any time where the multiplier of the growth factor is greater than 1. So this models any time where a, which is the growth factor here, is greater than 1. This function models any exponential function where a is between 0 and 1, like this, or 1/3, 1/5, etc. So we have discussed this also previously. This function looks like this. That. And it's a mirror image of this actually across the y-axis. And it also has an asymptote, and this the x-axis. You also never cross the x-axis over here like this. Okay, never do that. So x is asymptote. X-axis is an asymptote again for this function. Now, this function models exponential growth. If things are growing exponentially, will be modeled by this function. Okay, and this function models exponential decay. Okay, for example, if bacteria are growing exponentially, they'll be modeled by this function. If the value of a certain house is depreciating exponentially, will be modeled by this this function. Okay, so the two parent equations y equals 2 to the x and y equals 1/2 to the x. Okay, so these will model any function that where a is greater than 1 These will model any function when a is between 0 and 1. Okay. We talked about one example of exponential growth, and that is the compound interest formula. And I'll talk about these specifically in the future, so I'm just going to briefly mention this formula now. This is a very specific condition that relates to banking, where interest is calculated compound in a compound fashion. So simple interest formula, okay, is this one, okay, which we didn't talk about, but this is the interest given on the loan. Let's say 12%. Sorry, that's the interest that's collected on the loan, okay, and this is the principal amount. This is the interest rate, and this is the time. So that's the simple interest formula. In other words, if somebody puts like $100 in the bank, okay, and after 1 year, okay, if the interest rate is 12%, okay, the interest collected will be 100 times the rate, which is 0.12, times the time will be 1 year. Okay, follow? That's the interest collected. It would be like $12. Okay, that's the simple interest formula. So the simple interest formula is this. Okay, and this is compound interest. In this formula, A here represents amount of money after a certain time t. Okay, so if somebody deposits $100 in the bank, how much money will they have after 1 year, 2 years, 3 years, 5 years, 7 years? That's time. So the amount of money they have in the bank is a function of time. Okay, so time is the independent variable, or x, and that's why this is an exponential function. So A is the amount of money the person has in the bank after a certain amount of time t. P is the principal amount. Principal amount. In other words, amount deposited in the beginning. In our example, like I gave was like $100. The money the person puts in the bank in the beginning. Okay, and R here is the interest rate. Okay, for example, I just made that up. 12%, for example, was an interest rate, or 6%, 6.75%, whatever. So that's the interest rate. Okay, and the very important thing here is n. Yeah. Let me go over here. Oopsie daisy. And get this color here. So n here is the only variable that occurs twice in here. Is how often interest is calculated. Okay, how often an interest is calculated. So if somebody, for example, deposits some money in the bank initially, like $100, okay, and if the interest is calculated every quarterly, okay, they'll calculate the interest 4 times in years. In the first quarter, they'll make this much money. In the second quarter, interest will be calculated this much. It'll be this much. In the third quarter, it'll be this much. And in the fourth quarter, it'll be like this much. If the interest is calculated every quarterly, it'll be like this. If the interest is calculated once a year, n will be 1. If it's calculated 2 times a year, every 6 months, n will be 2. If the interest is calculated quarterly, n will be 4. If the interest is calculated monthly, n will be 12, like that. Okay, and you can almost surmise over here that this is kind of like exponential kind of growth type of a graph. Okay, so again, as a summary, this is the compound interest formula, where A is the amount of money a person has in the bank at any given time. P is the principal amount, the initial amount. R is the interest rate. N is how often the interest is calculated. T is the time. So if somebody, for example, deposits $100 in the bank and the interest rate is 12%, okay, and it's calculated quarterly, that means N is going to be equal to 4. This formula will become 100 times 1 plus R is going to be 0.12 over N, which is 4 times 4 times T. So this will be 100 times 1 plus 0.03 plus 4T. And you can simplify this further. 101.03. I'm hoping I'm do the math here. 4T. So this will be the formula for calculating their amount of money they have. Now, if you wanted to find out, for example, how much money will they have in 7 years, you will do this. 4 times 7. Okay, so let's just do that, and then to finish off, don't need this anymore. So it would be 100, not 1,000, times the quantity 1.03 to the exponent of 7 times 4, which is 28. 7 times 4 is 28. I got that right. So that's going to be that much. After 7 years, it's going to be $228.79. Okay, that's how much money they will have in the bank. Okay, so that's an example of how interest is calculated here. In the next time, inshallah, I will actually give specific examples of exponential growth and exponential decay models. One thing I do wanted to point out in this particular formula is you can see how this is exponential growth formula, because A here, the multiplier is greater than 1. So this whole thing is a model of exponential growth like this. Now also understand that this is real life, right? So time starts at time 0. This graph doesn't exist because like time, negative times, you're not going backwards in time. So this graph will kind of look like, at least theoretically, will look like this. Okay. So the domain here is restricted. The domain is going to be t is going to be equal to greater than or equal to 0, like that. Okay. Right, and the range, what's the range? The range, which is the y value here, A is going to equal to greater than or equal to 100. Okay. All right, so inshallah, next time we shall continue with exponential functions, and we'll elaborate next time by giving further examples, inshallah. Until next time, then, salatu wassalamu ala rasulillah, alhamdulillah.